So last time, quick review, if you had a surface and the surface may be given to you explicitly or implicitly, you have to be able to handle either case. And by the way, I give one of each on the exam. This quiz that's coming up, just to test you, see if you're getting it, and also the midterm and the final. So let's say you had some capping surface here just to make it sort of easy. And if it's given to you explicitly, then it's given to you as fxy equals something. That's explicit. Or it might be given to you in some big equation where you've got x's and y's all over the place. And, you know, your surface is given implicitly, which could look like a really hot mess. Let me just see if I... nope, that wasn't what I wanted to do. Nope, I didn't want that either. Let's see, I had it up and it disappeared. Okay, hang on a second because I wanted you to see some really kind of fun surface. And it looks like, oh, here it is. That one. I don't know if you guys, can you guys see that okay on your screen?
Non-Euclidean forms.
Yes.
Okay, so I want you to look at the equation for that interesting looking surface. Isn't that cool? That surface, there's no way, even if you were, you know, 2 PhDs in mathematics, you couldn't write it in explicit form. You know, good luck on trying to solve for z. You couldn't do it. There's a z squared, and notice that z is also contained inside the argument of a sine function. So you wouldn't be able to solve for z. So it's going to have to stay implicit. But you could still talk about slopes in the x and y directions, which you learned how to find implicit differentiation derivatives. And, you know, what's really cool is let's just see here, the directions are, let's see if I can, well, can I do the slider? No, that slider doesn't work for this one. So if you look there, oh boy, I zoomed in too much. So I zoom out here. So that's just an interesting looking surface where, yeah, implicit. Okay, so back to here. How would you deal with that? What would be step one before you try to go do getting the tangent plane equation or anything like that? Does anybody remember from Monday's
lesson? Set it equal to 0?
Yeah, you need to get everything on one side and 0 on the other. So it looks like a function of 3 variables, f, x, y, z, equals 0. And the same goes for explicit. So what I'm trying to say in my own sweet way, if you fail to do step 1, I don't even grade the rest of your problem. Even if you know, might be lucky and have it right. So if it's explicit or if it's implicit, like this crazy one that you're doing here, and if you could please mute yourself, it'd be great. I hear a lot of riffraff in the background. So you want to get everything on one side and 0 on the other. And then once you have this general representation, which is like a level surface for a function of 3 variables. So this is the level surface for a function of 3 variables. Where, and you know, to get level curves, you set the function equal to a function of 2 variables equal to a constant. And some of you blew that quiz problem out also. The one where you had to draw you had multiple choice, pick the level curves. And some of you don't know how to find level curves still. I'm pretty disappointed, I must say, because that was 15.1 material. Level curves, you set the function of fxy equal to a constant. Level surfaces, you set the function fxyz equal to a constant. But here the constant is 0. So instead of k, we're taking a specific level surface where the k is 0, not just a family of level surfaces. So this is known, aka, as the general representation. And once you have your function in general representation, whether it's given to you explicitly, so here you just subtract z from both sides, you could get your 0 on one side. Once they give you a point, the gradient del big F is a vector that's normal to the surface. And you can use that big old gradient to get the equation for your tangent plane, or if they want the parametric equations of a normal line to the surface, where the normal line is just piercing the surface normal to the surface there, use your gradient as the direction vector, okay? So now it's going to look like we're taking a slightly different turn here. but it's really just a continuation of the tangent plane discussion with differentials and change. Excuse me. Let's do some Math 250 review, because I have a feeling a lot of you forgot what differentials were used for and how to do a Math 250 problem. So this is my gift to you. You're welcome. So Math 250. So what's a differential? The way they would do it is they'd say, oh, it's the product of the derivative times the dx, which is like your change of x, and it's denoted dy. So in other words, using these two together, when you studied it, they probably gave it to you like this. dy, the differential of y, where y is a function of x, is f prime of x dx. Now, what did you use the differential for? You used it to approximate changes in your function. dy is like delta y, the changes of the y coordinates of your function. And it was a good approximation, because when you compared it to the actual change, which is denoted delta y, is simply the function evaluated at if you're looking at your interval, the rightmost endpoint, minus the function evaluated at your leftmost endpoint. And that gives you the actual change in y. But if you compare delta y to dy, usually they're pretty spot on as long as your x differential is small. So the other thing is, before I give you number 3, I don't want to go over that yet. Do you recall from Math 250 when they asked you for the equation of a tangent line? And we did this the other day. Remember? Y minus y1 is equal to m, x minus x1. Please say yes.
Yes.
Okay. And the m was f prime, wasn't it? Please say yes.
Yes.
Okay.
Yes.
Then what we're saying here is we're saying that x1, y1, the coordinates of the actual point you're trying to find the tangent line to, they give you some point where x is equal to a, and then the y coordinate of that point on the graph would be f evaluated at a. So your tangent line equation, this is still Math 250, folks, would have this look to, oops, sorry, I just blew it. Y minus the y coordinate, f of a, is equal to f prime of x times the quantity x minus a. Okay, and your slope would actually be f prime evaluated at a. Okay, now if you rearrange this equation by adding f of a to both sides, I hope you can see that the equation of the tangent line has this kind of look to it. Does everybody see this? So in number 3, when they're saying, oh, the linear approximation of the function at some point x equals a is this linear function right there, I don't want you to think that's any different from the equation of the tangent line, because it's the same darn thing. Instead of y, though, there, they just replace the y with L of x. What do you use that for? You use this linear approximation to approximate your actual curve. So the picture in Math 250, in case you're losing sight of what you studied in Math 250, I know it's been a while, but let's say here's the point when x is equal to a, and they're finding a tangent line. If you stay pretty close, in a pretty close neighborhood about the x equals a, this straight line almost approximates your curve. I mean, they almost look like they're coincidental. And that's a good thing, because you can use your equation of your line as a very good approximation to your actual function. They're almost one and the same, as long as you stay in a tight neighborhood of x equals a. So that's the point. So let's just do a quick problem for Math 250. So letter A, find the differential of y when x goes from 1 to 1.01, and then compare this to the actual change of the function. So if we're going to use differentials, this is Math 250. I'm going to go pretty quick here. Let's see, the derivative of x squared. Oh my goodness, that's easy, 2x. And then when we're finding the differential as x goes from 1 to 1.01, we're going to plug in the value for x. Now here's the question. Let's see if you guys remember your Math 250. Do I plug in the starting point 1, or do I plug in the ending point 1.01, or does it matter?
I don't know.
Nobody has an idea, huh? Gee, I wonder
I
what
have
would
ideas, but they're
happen.
I wrong.
I wonder what would happen if I gave a Math 250 final to you guys. Would you guys pass it? Oh, goodness. Oh, dear. Okay, it turns
It would
out.
be a gradient question where you just find the like lowest possible grade and you just apply that to like the projection of what's going to occur.
Okay, let me get my mind around that one. Turns out you do it at the starting point. Okay, so your dy is you're gonna plug in x equals 1 into this mess. So your differential is going to be 2 times 1 times delta x, but delta x is really the same as dx. So you're just going to do the difference. Take the difference of those x values. So you're going to get 2 times 0.01. And this is equal to 0.02. And that's the approximate change of y as x starting at 1 and then x goes to 1.01. Y will change this much, 0.02. Now, is that a pretty good approximation? I don't know. Let's do actual change of y. So the actual change of y, which is denoted delta y, is simply the function evaluated at that rightmost endpoint, 1.01, minus the function evaluated at the leftmost endpoint. Now this function is easy. It's just y equals x squared. So what's 1.01 squared minus 1 squared? Go get your calculator and whip it out. And I get the actual change of y is 0.0201. Now I want you to compare these. Are these guys pretty close to each other? What do you think?
Yes.
Yeah. So what's the point? So the point is that you were supposed to learn from Math 250, in case you forgot, is that the differential is a pretty good approximation for approximating changes of y. It's almost the same, not too bad. Now, the last part of this Math 250 review is, and by the way, I'm doing this for your benefit, not mine, because in order for you to appreciate and understand the analogous version in Calc 3, you have to kind of know the Calc 1 version. Otherwise, what am I doing? Just feeding you a bunch of stuff and, forcing it down your throat, and you really have no idea what the heck is happening to you. And I don't like learning like that, and I would certainly think that you wouldn't. And so that's why I'm doing this, okay? So here we go. So we're going to find the linear approximation function of y equals f of x at the point when x equals 1. That's a Calc 1 problem, folks. They're basically asking you to find the tangent line equation and use it to approximate f evaluated at 1.01. Okay, so if we use this idea of that linear approximating function, so you have f of a plus your derivative evaluated at a, and x minus a. This is basically the equation of the tangent plane. And so for us, for this function, the a is the starting point, so f evaluated at 1 plus f prime evaluated at 1, and then multiplied by the quantity x minus 1. Okay, so then this is, well, f of x is x squared, so this is going to be like 1 squared, which is 1, plus, and I think we saw that f prime of 1, which is up here, 2x, that's 2 times 1, and then x minus 1 looks like that. So your approximating function that you can use for any value of x, although it's preferable if you stay close to x equals 1, because then the tangent line doesn't work as a really good approximation for the function. And now if you substitute x equals 1.01 into this tangent line equation, what do you get? So you get that y is equal to 1 plus 2 times 1.01 minus 1. And so the y value that I get after I punch this all up is 1.02. And then, and so that's basically the value of the tangent line y coordinate when you plug in x equals 1. Well, what about the actual function? What about the actual function evaluated at 1.01? We already know f of x is equal to x squared, so what's 1.01 squared? Well, it's 1.0201. So these are pretty close. So what are we saying? That tangent line, that's, this function here, is a pretty darn good approximation of your function, as long as you stay within a close neighborhood of the point that the tangent line is for. So we're going to have a similar, so the answer here is they're the same. Is it the tangent line? Yes, it's the same. So back to Math 252. So the analogous differentials in Math 252. So let me just walk you through it, talk you through it before we do it. So we're just going to have a function of two variables, which you could see that the graph could be a nice surface that would pass the vertical line test. And if you had a tangent plane at a point to that surface, the tangent plane is a really good approximation of the surface. And I think I showed you the other day when we were looking at my graphs, you know, let's say you pick a point here and you've got a tangent plane to it right there. As long as you stay really close to that point, the flat tangent plane almost coincides with the curvy surface, that paraboloid, and you can use that tangent plane as a good approximation tool. And that's the point. So let's do some definitions. So the starting point here is if you've got a function of two variables and delta x and delta y are increments of x and y, then the differentials of these independent variables x and y are dx and dy, where dx is approximated by delta x. That's the analogous to Math 250. But you got another one, your change in y is delta y. So your total differential, which is denoted dz, is equal to the partial of z with respect to x times dx, which you could use delta x for. So these are almost the same. Plus the partial of z with respect to y multiplied by dy, where the dy is essentially the same as your delta y. Okay? So that's your total differential. What do you use this for? You use it to approximate changes in z. So use to approximate changes in z. And it's a pretty good tool to use for approximating. Now the actual change in z is the actual altitude change, because z coordinates give you sort of the altitude corresponding to a point. And so the actual change in z, which will denote delta z, is simply the function evaluated at the x plus delta x, y plus delta y, minus the function evaluated at the starting point. So x and y is usually the start point. And we don't have intervals here, so we just have starting points and ending points here. So that's it. And so these are usually pretty close if you compare, as long as your fixed point, it stays pretty close to the other point. Otherwise, the approximation isn't so hot. Okay, now similar to what we did up here, where we had this approximating function up here, this L of x, which is a sense just the same as the tangent line. It was the same. So don't think, oh, L of x, that's something new and improved. No, it's not. It's just the freaking tangent line. Okay, so for us, they're just going to rewrite the tangent plane. So let me remind you that if you had z equals f of xy, like this, and you followed my lead, where I told you to get everything on one side and 0 on the other, and this is your fxyz. So you basically have fxyz equal to 0. And remember that your del f, which is this guy here, this gives you a normal vector to your tangent plane. This was last class. And if you were asleep on Monday, I apologize, but you better get with the program. Otherwise, this coming week's quiz is going to be hurt. But it turns out that big fx ends up being the same as little fx here, just because you just move some stuff around. And this ends up being the same as fy if you know your original function was explicit. And then since I moved z to the other side, and there's only one z in this whole equation, the derivative with respect to z is going to be -1. Or it'd be +1 if you moved all the junk to the other side, okay? Either way, this is going to be your normal vector. So when you do your tangent plane at the point AB, f of AB, if I do the standard form, it would be f of x, fx essentially evaluated at that point, times x minus a, plus fy evaluated at the point, times y minus b, plus -1 times z minus f of ab, because that's the z coordinate of the point that you're finding, equals 0. And then if you rearrange this mess and you solve it for z, like I'll distribute the -1, so I have negative z, and then a minus minus is a plus, f of a, b, and then you add z to both sides, you will get this right here, where L of xy is your z. So it's basically the same as the tangent plane, and you're going to use that tangent plane as your linear approximating function. Okay, so if we do some examples here, so here's a problem you might see on MyMathLab. Okay, so find the linear approximating for the function at the point -1, 4. So basically, they're just saying this is the same as finding the tangent plane equation. This is a fancy way of asking you to find the tangent plane equation at the point. Now here's the thing though, -1, 4, and then how do I find the z coordinate? Because you need a z coordinate because it's in space. You've got some surface here. This actually is a looks like an upside down paraboloid. Anybody know how to get this z coordinate for the point?
Just plug those into the function.
Good. Yeah, your z coordinate will be f evaluated at -1, 4. So I'll just put f evaluated at -1, 4. Okay. So so I'm going to get everything on one side and 0 on the other. So step 1 is I want to see this general representation. If I don't see that as step 1 on your handwritten work, you will be losing points. And don't tell me you did it in your head. I want you to get used to doing this. And I don't care which side of the equation you get everything on. Just get it on one side. So if I subtract z from both sides, I've got this. This is essentially my big function of 3 variables. Then the normal vector to the plane, to the tangent plane, is going to be the gradient. This is equals the gradient, the 3D gradient. So for us, if you go get the partials here, the partial with respect to x of 12 minus 4x squared minus 8y squared, I think that's going to be minus 8x. The partial with respect to y is minus 16y, and the partial with respect to z is -1. Okay? When I evaluate f at -1, 4, so I'm going to have to do a lot of substituting here into the actual function itself, and then use your calculator, I get to -120. So the z coordinate of your point is going to be -120. So the standard equation for your tangent plane, well, wait a minute, we're not ready yet. Sorry, I'm missing a point. I'm doing this common student error. They give me a tangent plane with the normal vector not being a constant vector. So I do need to evaluate my gradient at the point -1, 4, -120. And so if I do the correct substituting here, -8 times x, and then the next component is -16 times the y, and then -120. Excuse me, I can't plug that in. It's just -1. And then let's see. So this gradient ends up being +8, -64, -1. So there's your normal vector to the tangent plane right here. And then when I use it, I go 8 x minus a -1, but that's x plus 1. And then the -64 y minus 4. And then minus a 1 times the quantity z minus a -120, that'll end up being z, equals 0. And then clean this up and rewrite it and solve this for z. I'm just going to go through this quickly because we're running low on time. You would distribute and collect like terms and all that hoo-ha. And then you should, after solving for z, get z is equal to 8x minus 64y plus 144. Okay? Now, in my math lab, when they have you type stuff up, they're probably going to call this L for linear approximating function, function of x and y. Okay, but it's your z. Okay, same thing. So they're going to go, hey, give me that linear approximating function. Then you'll see this big LXY. You're going to go, what's that? And nothing different. You're just going to find your equation of your tangent plane, all the usual that we did on Monday, and then just solve it for z, and then rename z LXY. That's it. Okay, now what? Use your answer to part A to estimate what would the function be if you evaluated it at -1.05 and 3.95. And you're like, oh, well, just substitute these coordinates into your brand new tangent plane function, basically. And then, of course, hopefully you whip out a calculator, because who wants to do this in their head? And ooh, I get negative 117.2, okay? And now, is that a good answer, like compared to the actual value? So the actual value is the original function evaluated at negative 1.05, 3.95, the coordinates at that point. So what's your original function? Well, they gave it to you way up here. Z is equal to fxy 12 minus 4x squared minus 8y squared. So I'm just going to substitute 12 minus 4 times, ooh, negative 1.05 squared minus 8 times, ooh, 3.95 squared. Ooh, good God. Get out the calculator, folks. And I get negative 117.23. So your job now is, what do you think? Is this a pretty good approximation?
Yes.
Yes.
Okay, I apologize if everything's getting a little bit fakakta here. Let me, it's probably my computer. I imagine it's on my end. So let me go ahead and kill off some of these things on my screen. Hey, while I'm here killing off some tabs, quick commercial break here. I want you to notice, for those of you who are still struggling with any material at all in the class, may I please direct your attention to my Canvas pages. And in my Canvas pages, look, I put all these videos. These are not me, but they're very good short YouTube videos on different things. So like if some of you, and I get that some of you are still not good at, you know, some of you even confessed to me, I don't really understand all that curvature stuff. Okay, well, after reading the book and rereading your course reader and maybe working a few more homework problems from the book, have you even considered looking at some of my videos that I have posted here? Okay, some of you still don't get level curves. Here you go. Here's level curves. Here's limits. Here's finding domains. Here's arc length. Here's something on the unit normal vector. And the next thing, most of you seem to get partial derivatives okay, but maybe you're still not clear about the chain rule. Here's some videos on the chain rule. Maybe some of you would like to see some directional derivatives then. Go watch those. And then here's some stuff about the gradient and level curves, how to get a gradient, finding a unit normal vector to a surface. That's what we're doing this week. Equations of tangent planes to a surface, an equation of a tangent plane to an implicit function, all this stuff. And so where are we now? Well, we're doing some week 8 stuff here. We're going to start finding critical points and stuff like that, hopefully today. Okay? So you always have that option of, you know, boosting your understanding, and I encourage you to go do that. Okay? So I hope that calmed down my video some. Let me know. I'll check the chat box. All right. So the writing has been super laggy. I don't know, it's called technology.
Professor, really quickly, your laptop's also kind of low in power. Or
Oh, you're
it
right.
will be very soon.
Thank you. Thank you. Yeah, see, this is really weird. Thank you. Let me put this on hold for a second. So how do you write the differential for this function? Okay. So after noticing that these, when you compare, it's a pretty good approximation, that tangent plane equation, pretty good approximation, I must say. It's awesome. It's almost as good as the real thing. So write the differential. Remember, the differential has this formula to it. Now, this formula, I want to caution you, it's not the same as the chain rule. It kind of looks like the chain rule, but I'm going to get very unhappy with you if you start doing bad notation on your handwritten work and go, well, that looks pretty much like the chain rule to me. Well, it isn't, because please let me remind you that the chain rule would be, you would be taking the derivative of the function z with respect to time. And you would have the partial of z with respect to x, but you would multiply that by the derivative of x with respect to time plus the partial of z with respect to y times the derivative of y with respect to time. And I know they have that same sort of look to it. And so I can't do anything else, David. I'm really sorry. It didn't lock itself into place. So I have no clue what you're asking, and I apologize. I'm just going to keep moving on. So just do the best you can, okay? So this is the chain rule right here. This is not the same as the differential. They're used for two different things. The chain rule is when you're doing like related rates, like, oh, I want to find the change of volume with respect to time when the ice is melting of the rectangular box. Different from finding the approximate change of a function where time isn't even involved. So please know the difference and try not to get too confused. So this is the differential. And if they wanted the differential at the point, so if they were saying, what's the differential at the point, say, -1, 4, going to, boy, this is kind of laggy, I don't know what to say. -1.01, 3.95, we're going to do that in the next part D. So let's do that. So how would you use this differential formula to find the change in Z when you move from this point to this point? So first you have to get your dx, which is essentially the change in x. You have to be careful here because order matters. You take the x coordinate of the ending point and you subtract the x coordinate of the starting point. Okay? And so I hope you notice here you actually are going to get a negative number, and yes, that can happen. So you're going to get a -0.05, I guess, here. And then your delta y is essentially the same as your dy. So you'll take the differences of the y coordinates. So you're going to go 3.95 minus 4. So I think you're also going to get a negative there, yeah? So sometimes your dy's and dx's are negative, not always. And so then when you do your dz here, you're going to go, okay, what is dz dx? And I think we found that was -8. So this right here was, if I plug in those partials that I did above, -8x dx plus the dz dy was -16y dy. So if I use that down here, I'm going to get -8 times the starting point x times your dx plus -16 times y, which is 4, times your dy. And you should get, if my things are correct here, I got 2.8. So that's your approximate change in altitude. So what's your actual change in altitude? Your actual change in the z coordinates? Well, you actually just plug them in. So delta z is the original function evaluated at -1.01, 3.95, minus the actual function evaluated at -1.4. And so I'll let you figure all this out. I'll just tell you that what I got is 2.77. So what could be garnered from all this? What's the summary? Pretty good approximation. Pretty good approximation. And so that's the whole point of differentials. You can use them to approximate changes in altitude. It's pretty good approximation. Okay. I don't have time to do the error analysis problem. I'm gonna move on because I do want to get to, it's a really nice usage of differentials to approximate propagated error. It's awesome. You can use it to, anytime you measure something, your measuring tool is always off by something. There's no perfect measuring tool in the entire universe, okay? So it might be off a little bit. And then if you try to calculate the volume of a box, where your width is going to be a little bit off and your length is even a little bit off and then your height is going to be a little off, what's the propagated error when you compute the volume? It's not what you think. So you find that answer by using differentials, okay? So I'll let you work on that. If you want me to do it, I'll be happy to do it during an office hour, okay? We're going to go to relative extrema because that's next on the agenda and we're running low on time. Really? Yeah. You don't believe me? I think we're behind all the other Calc 3 folks. They're ahead of us. I'm always slow. Okay. And if you think we're going too fast, think about that. Like, really? We're slow, yeah. We're slow. Okay. So one of the most important things that you can do in this class is find extrema. And you did it in Calc 1 a lot. So now you're going to do it in Calc 3. And it's really fun. Isaiah, I agree with you. Yeah. Okay. So let's go ahead and save this to a nice PDF and get going. Well, that's the wrong file. Sorry about that. I don't know where I got that from. Huh, that was weird. What happened? I thought I did Math 252. I got something else up here. That's very strange. It looks like Calc 3, doesn't it? That's Calc 3. And maybe when I saved it to a PDF, it named it something else. Did anybody catch that, or did I not focus up enough?
I can't tell. Just like tabs are flashing. It's like laggy.
Huh. Okay.
It's a very retrobate approach to Calc 3, to say the very least.
Let's see here. I don't know. Okay, this looks like what the file that I want. Okay. So my power is now on. Is everything still pretty laggy?
I don't know. If
It comes and
my
goes.
internet.
Comes and goes? Okay, so let me try to kick off some other software that might be taking up too much cache memory. I don't know. Okay, I've got a lot of, everything's kind of gone. I'm pretty much now limited to PDF annotate. Well, I guess I could get rid of this. Let's just get out of here altogether. There we go. All right, so what about Extrema? So what did you do in Calc 1? So when you were in Math 250, aka Calc 1, quick review, there were two types of maximums and minimums they would ask you to find. One of them was relative and the other one was absolute. So I just want to remind you about the difference between relative and absolute, so you kind of have a handle on that, and it seems like a lot of us need some review on Calc 1 anyway, so it's a good thing. Okay, so let's just say on the interval a to b only, let's just limit it, okay? It won't be from negative infinity to positive infinity. You had a nice graph here like this, okay? This is Math 250. And let's say this curve is described by y equals a function of x. Okay, fine. Now what? Well, it turns out that on this interval a to b, this point here is a relative minimum. And not only that, it's also the absolute minimum. Why is it both? Because it's the lowest, it has the lowest y coordinate compared to all the other points on the graph. Okay, so it's also the absolute minimum. On the other hand, if you were looking for maximums, this point right here is what we call a relative maximum, but it's not the absolute maximum on this interval. Why not? Because right here at the rightmost endpoint, this y coordinate here is even taller than him. So this point here, you would denote the absolute max. And I hope you guys can appreciate that sometimes your absolute max is the absolute relative. Like if you looked at, let's say, an upside down parabola like that on any interval, this vertex here is both a relative and an absolute max. So it's both. Yeah? On the interval, say negative infinity to infinity, you know, it's going to be both. So just another quick review. When you took Calc 1, how did you go ahead and find relative maximums and relative minimums? So the procedure, just a quick reminder, because our procedure will be similar but not exact. You remember you found the derivative?
Yes.
Yes.
Oh yeah. And then you went to find what's known as critical points. Well, what the hell are critical points? Well, there were two types. One type, which was the usual type, is you would set your derivative equal to 0 and find the values of x that made your derivative 0. But you could also get other critical points, which are not as common, say, but when does f prime of x equal undefined? That would also give you some critical points. Now, the critical points were no guarantee of you having a max or a min. Remember that? You actually had to do some extra work. And so what was the extra work to show whether or not you had a max or a min, or sometimes it was neither? Those critical points, there's a theorem, and we'll do a similar theorem, is that if you are going to get a maximum or a minimum, they can only occur at critical points. But the reverse is not true. Just because you've got a critical point in hand is no promise or guarantee that it's going to correspond to a max or min. Remember, sometimes it would correspond to like an inflection point or something like that. I don't know if any of this is ringing a bell, but it's good for you. So the extra work would be you'd either perform the increasing decreasing test, which I love. That's where you make a big old table and you do this interval summary table and see if the, if f prime is increasing before the point, f prime is decreasing after, then you have a max. And if it's decreasing before but increasing after, you have a min. Those kinds, that was my favorite way. Or you were able to do the second derivative test. So one of those two tests had to be performed in order for you to distinguish if you had a true relative extrema in hand, okay? So good news, you're not going to be making any interval summary tables in my class. You are going to do something that's analogous to the second derivative test, but it involves a little bit more work than the Calc 1 second derivative test. Okay, so let's do a quick couple definitions here. We're just going to define what is a relative max in the world of a function of two variables. Well, it's just the tallest guy on the block. That's the non-technical way of defining it. And that's basically the non-technical way of defining it in Calc 1. Whoever had the highest y coordinate on the block was the max. And then similarly, instead of on an interval, we're going to look over a disk, if you will, or a region. So relative mins are the shortest guy on the block. So that guy is the short guy on the block. And instead of intervals, again, it's open disk. Okay. And then if you've got a max on your hand, well, see how it's greater than everybody else? So he's the tallest guy on the block. Okay. And that's the quick definition. Okay, now, you have to be careful when you're finding relative maxes or relative mins. There could be more than one. Just like when you took Calc 1 and you had a function that maybe looked like this, heck, man, look at all these maximums you had. You had to go find them all, right? If they had, you find negative infinity to infinity was your interval, and look at all these relative minimums. Oh my goodness, there's more than one. Well, similarly for us, our surface could have lots of peaks and valleys to it, and your job is to go get the peaks, that's the maximums, and then go locate the valleys, which are the minimums. Okay, and that's a kind of a nice bumpy surface there. Kind of looks like a mountain range. So that's your job. So how do you go do that? Okay, so let's define what a critical point is, and then we'll go to the big theorem on the next page, and then we'll do some prep work, and then we'll hit the big theorem. Okay, in that order. So here we go. For us, a critical point is similar to a critical point that you had in Calc 1. So that's the good news. You don't really have to learn much new, okay? So what is the critical point for us? Well, first you got to have your function f be defined on some open region, otherwise forget it. And you have some fixed point that you think is a critical point. Really? Well, what really makes it a critical point? Here's the definition. If when you substitute that point into both of your first partials, it makes both of those first partials go to 0 simultaneously. If one of them goes to 0 and the other one goes to some other number like 2, forget it. It ain't a critical point, okay? Now, the other critical point, which is less common, this is similar to the undefined, is where when you substitute that point you think is a critical point into your fx, it makes it undefined, or, so this is an or statement, you plug it into the other partial, f with respect to y, and it's undefined. It could make both of them undefined also, either or. So that's a critical point. Let's look at it geometrically and visually. So if you have a function that's differentiable and your gradient evaluated at that point is 0, 0, then that means every directional derivative is 0. Yeah, your slope is 0. Well, I hope that makes sense, because remember in Calc 1, when you found a relative max or a min, wasn't it true that the slope of the tangent line was 0?
Yes.
Yeah. So here your gradient is 0, and so all the directional derivatives in any orientation are 0. So if you look at this picture here, I want you to notice that this looks like a relative max. It's got a little bump there on the blue surface. And when they put a little tangent plane there, that's that little red portion of a tangent plane, do you notice that the tangent plane is horizontal? Please say yes.
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 So what would that mean big del F is? Because big del F, remember, is a normal vector that's punching out of the tangent plane. It turns out that big del F, as I mentioned, when you have your function described explicitly and you get everything on one side and you subtract z and 0 on the other, it's going to look like little fx will be the same as big fx, partial with respect to x, little fy, and then you'll have a -1. So actually your gradient will be punching down. And if you did the reverse, you'd have this. If you did want your gradient punching upward. It doesn't matter when you're trying to get a normal vector to a tangent plane, though, you just need a normal vector. Okay? And so I hope you get that for this tangent plane, the fx and fy will be 0. Does that make sense to you? Do you get that this looks like, k hat, pointing straight up?
Yeah, that makes sense.
Yeah, that makes sense.
Yeah. Or negative k, this guy is negative k hat. So your tangent plane is horizontal, which means your normal vector will either be k or negative k. So pointing up or pointing down, your choice. And so similarly, the next picture is just when you have a valley, same thing, you'll have a tangent plane that's horizontal. And so the big del F gradient will be 0, 0, 1 or 0, 0, -1. But the key point I want you to get is the first two zeros there are your fx and your fy. So when you find one of these critical points, and that's what we're going to be doing, and hopefully a few examples today, you need both partials, the small partials, little f, x and little fy, essentially, to be 0 simultaneously. And that'll give you that horizontal tangent plane. Okay, so here's the theorem. This pretty much says the exact same thing as your Calc 1 theorem. Exact same. That if you are going to have any relative extrema at all, they can only occur at critical points. You can't all of a sudden get some weird point from outer space and go, well, I think this point has a max also. No, it can't happen. It can only happen at critical points. So, but the reverse is not true, so be careful. And the reverse was not true in your Calc 1 class also. Same thing. Okay, now I'm going to do some prep problems. And when I say prep problems, these are kind of cheesy and easy and sleazy. And we're not going to actually do what I'm doing here because I'm going to jack it up and we're going to do the full dish soon. But I just want you to get a feel for maxes and mins. So real quick, here's a function, 1 plus x squared plus y squared. And more importantly, I want you to get that this is the same as z equals 1 plus x squared plus y squared, like so. Okay, fine. So does he have any extrema? Well, I don't know. Go get your first partials and then simultaneously set them equal to 0. And folks, when you do this, you basically get a linear algebra problem, although this is kind of a trivial linear algebra problem. You're going to get 2 equations and 2 unknowns. So sometimes you'll get a nonlinear system of equations, but this is a linear system. So this is pretty easy to solve. Well, really? Yeah, like, what's the answer? Well, I hope you could get that when you solve for x and y, you'll get x equals 0, y equals 0. So the point 0, 0 is indeed a critical point. Now the question is that critical point giving us a max or a min? And it turns out if you graph this surface, you will get an upward facing paraboloid with a vertex there at the point 0, 0, 1. And yes, at the point 0, 0, you get not only a relative min, but an absolute min. Right there. Okay? So that's sort of a cheesy problem because you didn't have to do much. Okay, let's do another cheesy problem. Check out this surface. 1 minus the quantity x squared plus y squared being raised to the 1/3 power. Okay. Does it have a critical point? I don't know. Let's go get the partial. And you know you're going to need the chain rule when you get your partials here. So fx is going to be negative 1/3 times the quantity x squared plus y squared to the what?
Negative
I'm going to call on somebody. How about Jonathan Trong? What is that raised to? You tell me. X squared plus y squared to the...
Are you asking what the problem says, or?
No.
Oh, right there, right there. Okay.
I just want you to tell me that one little exponent, and then after that, tell me your favorite color.
It's 1/3 minus 1, correct? So
Okay.
it's negative 2/3.
Perfect. And your favorite color is?
Blue.
Okay. All right. Good choice. That was the right answer. Thank you. Okay. Am I done taking this derivative? No, because you got to use a chain rule. Now you got to differentiate x squared plus y squared with respect to x, right? So what is the derivative of x squared plus y squared but with respect to x? Jordan, you tell me. The partial of x squared plus y squared but with respect to x. That's going to go right here. Are you there?
Yeah, I'm here. 2x?
Yes. Beautiful. And then I don't like negative exponents, so I would appreciate when you rewrite this, just make it look a little pretty. You know, rewrite with positive exponents so it looks good. You don't have to do rewriting with positive exponents for exponentials, though. E to the negative 2/3 I'm totally okay with. Okay, you're going to do a similar thing for the other partial, so I'm going to just whip through this using the chain rule, only this time you'll have 2y, and then when I clean this puppy up, I'll have this. Okay, fine. So now the question is, do these guys equal 0? Well, you could go, well, when do these equal 0? Well, when does a fraction equal 0? Well, when the numerator equals 0. Okay, when does negative 2x equal 0? Well, when x equals 0. And you could do the same thing here, but there's a problem. Because here you could go, well, this is the same as the last problem, 0, 0. But I claim if you punch 0, 0 into the denominator as well, both of these partials are actually not equal to 0. They're undefined. Why? Because 0 over 0 is indeterminate. So these are really undefined at the point 0, 0. And that's okay, because this 0, 0 is still a critical point, because the definition said, if you go back to the definition of critical point, if you have your partials undefined, hey, that's a critical point too. Cool. So if you graph this thing, and this is the letter B surface, I just want to show you what the graph is. It's kind of cool. It looks like a Hershey's kiss. And so if you graphed it, it kind of looks like that. And at the very tip there, you can see it's like a sharp corner. That's why your partials are undefined there, because the derivative is pretty much undefined. At that point, 0, 0, 1, though, you do have a max. Okay? And now the weird problem, and this is, you'll see why I'm doing this whole setup of all these cheesy problems. What about this thing? This thing here, y squared minus x squared, is not like a paraboloid or anything like that. It is one of the quadrics. Do you guys remember? Does anybody remember what the graph of this is? And I wouldn't expect you to, because you know I don't have all those quadrics memorized either. Are you kidding me? Hell no. So if I why would I try to memorize all of that? So I'm going to go y squared minus x squared. Let's just take a look at the surface. I mean, how bad could it be, right? Woo! Hey, check that out. Ooh, that's kind of lovely. Since this is an explicit function, my software lets me have access to more colors than implicit, which is kind of nice. And, you know, I can still go solids. But I kind of like all these. Woo, wow, that looks really cool. Okay, so there's a surface. Now, does that puppy have a max or a min? Well, let's go get the partials and set them equal to 0. So if you get fx, you're going to get negative 2x, and then fy is 2y, and then you set them equal to 0. It's 2y. You set these equal to 0, and you go, oh, what does that mean? It means my laptop's too slow. 0, 0 is a critical point. Well, is there a max or a min at that critical point? And if you look at the surface that I have graphed for you, you know, 0, 0 is occurring like right there where my cursor is. It doesn't really look like it's going to be a max or a min. It's kind of weird. And so here's the part that I want you to get. So there at 0, 0, and I'm going to try to draw the surface here, but a little extra for you just to be weird. So check this out, checker outers.
Okay.
Okay, now I'm just trying to draw a horse here. Okay, I know. I'm just bear with me. All right, I'm not that good. Okay, you know, huh? Nice horsey. Okay, all right, there he is. So why am I drawing a horse? Am I just trying to be ridiculous here and waste your time? Of course not. I would never do that. But here's what I want you to see. Here at the point 0, 0, 0, if you pet your horse in this direction, it looks like that point is a minimum, you know, if you're petting your horse in this direction. But if you pet your horse along his girth, so this way, I hope you could appreciate like this, you know, over his sides, it kind of looks like that point is a maximum. So which is it? Is a min or a max? Well, it's neither. We actually have a name for it. It's called a saddle point. And that's why I drew a horse for you, because he's wearing a saddle. And if you look at the surface, which I think is a hyperbolic paraboloid, so that's what I want you to get from that. So that's cool. And why do you care about saddle points? And my internet may go out any minute. I'm going to warn you in advance. If I disappear, stay on the line. I'm coming back, okay? I don't know what my internet's doing today. It's not happy. See what's going on here. Says it's secure, but you never know. Some days it's unhappy. Okay. Do you have to write this? Yeah, write down saddle point, Isaiah, right now, because you're going to be worried about saddle points. Here we go. Here's the theorem. This is known as the second partials test. It's kind of like the second derivative test in Calc 1, but it's like it's on steroids. Are you guys still there?
I'm here.
Yeah.
Yeah, we're still here.
I just checking. Okay. So why do they call this the D test? D stands for determinant, and I'll show you why after I'm done with the theorem. So just remind me. And linear algebra people, pay attention. Okay. So you're going to have a function that you're trying to find your relative extrema for. And you find this point AB where the partials are simultaneously equal to 0. So you find your partials, you set them equal to 0. Now, folks, this is the hard part. I claim out of these problems, this is the hard part. I'm telling you in advance. So as a student, I'm giving you fair warning that when I give problems to students for these problems, they bomb out because they can't find the critical points because their algebra skills are weak. When you set these two equations basically equal to 0, you will have to solve either a linear or, and this is the hard part because you linear algebra people, this ain't going to help you, or a non-linear system of equations. Nope, don't want to go there. Non-linear system of equations. And you should have covered this in a pre-calc class or something of solving linear and nonlinear systems. And you can't really, I don't want to see matrices involved here for, you know, these nonlinears because you can't really add unlike terms to each other. The best way to solve these typically is going to be using the substitution method, and we're going to do that, so don't worry. So after you get your critical points, and there may be more than one, to test to see if it's a max or a min or a saddle point, or it could be inconclusive, you have to do some tests. You first have to create or form this quantity, and it's called the D quantity. That's why they call it the D test. And so it's fxx, these are second partials, people, multiplied by fyy minus fxy squared. Now, do you notice that one of the second partials is missing? Didn't we used to get 4 second partials? I mean, I asked you for all 4 on
yx.
Yeah. Why is yx not there? Does anybody want to gander a guess on why they discriminated against the fyx second partial?
The second derivatives are equal to each other.
Very good. Fyx is essentially the same as fxy if you've got continuity. That was one of the theorems. So we're actually taking both into account because we're squaring fxy. You can almost think of that as fxy times fyx. Essentially it is, because I'll now tell you why they call it the D test. You're actually setting up the determinant fxx, fxy, fyy, fyx, and you're taking the determinant of this. And if you recall, when we do the cross product, you were taking determinants. So you take the, oops, sorry, this is backwards. This is supposed to be fxy, fyy. You're taking the product along the major diagonal, and that would be this right here, minus the product along the minor diagonal. So that's what your D stands for, and when you look at other calculus books, they typically call it D. I'm not sure if Briggs does, though, because, you know, Briggs knows what's going on with Briggs. Whatever. Okay, then if your D is positive, then you have to double check your fxx evaluated at your critical point. If it's also positive, you have a relative min. Now keep in mind that's weird. It's almost backwards. Your D has to be positive and fxx has to be positive. Then you have a rel min. On the other hand, if your D is positive but your fxx is negative, you've got a rel max. If your D is negative, don't even bother looking at fxx because who cares? Immediately you can conclude saddle point, and now you know what a saddle point is. It's sort of like the analog for an inflection point. It's not a max or a min, but it is cool. And then if your D is 0, your test is inconclusive. This doesn't mean there aren't any maxes or mins. It means you may need to go get a computer system and or maybe a grapher and try to look and figure out if there's a max or a min that way. Okay, so now time for examples. Okay. Everybody still there?
Yeah.
Yes.
Yay! Math 255 is nonlinear algebra. There is no such thing as Math 255. Come on, David.
There is no.
Don't scare people. There's no such thing. Okay, so we're going to look at this function, and we're going to see if it has any extrema or saddle points. All right. Here we go. fx and fy. That's step 1. You know how to find partials. Let's see, the partial with respect to x, we'll have 2x plus 1 minus 3y, and I'm going to set that equal to 0. The first partial with respect to y is 3y squared. And what else? Minus 3x, and I think that's it. Set that equal to 0. Okay, great. Now what? Folks, this is a non-linear system of equations. Not a linear system, it's non-linear. How do I know it's non-linear? Like what's the key thing that tells me, oh, this is not a linear system of equations?
The degree of the functions.
Yeah, this 3y squared, if that weren't squared, then this would be a linear system, but that squared messes the whole system up. So it's a nonlinear system. Now, the best way, and I'm going to say this at the risk of being redundant multiple times, the best way to solve systems of nonlinear systems is by substitution. So how do you do that? Well, pick which one of those equations is the easiest one to work with, solve it for one of the variables, and then plug that into the other equation, and then try to find one of your coordinates. So I know a lot of you may think that the first equation is easier looking because, hey, you know, it's linear, it's probably the best one to work with. But the problem is if you use it to solve for either x or y, your choice, I don't care. You're going to get a fraction. And then when you plug it into the other equation, you're going to have all these freaking fractions everywhere, and it's a nightmare. So I claim, even though it seems counterintuitive, that if you solve for x with the second equation, that's the partial with respect to y, this is easy. I'm simply going to add 3x to both sides, and then I'll divide both sides by 3, and I'll get that x is equal to y squared, and then I'll substitute x equals y squared into the other partial. So what is the fx going to look like when I substitute x equals y squared? So what that looks like is we'll have 2x, but that'll be 2y squared, plus 1 minus 3y equals 0. And this is an equation that only has one variable in it. That's good news, because we'll at least be able to get the y coordinate of our critical point, which is awesome. And then we're halfway there. So then, oh my God, I'm just reading the chat box. That's hilarious. So I hope you guys can recognize that this is a quadratic equation. And please don't break my heart and try to isolate the y and act like you've never taken an algebra class before, because I'm going to get really sad, okay? A quadratic equation, folks, when you solve it, please don't forget your basic algebra. You can use the quadratic formula, of course. That's a little bit overkill, though, at times. And also, it's prone to error, because sometimes you get your pluses and minuses all messed up. I claim this actually factors. So the key number is 2 times 1, because I multiply the leading coefficient with a constant. And the factors of 2 times 1, which is 2, that add up to -3 are -2 and -1. So my bingo numbers are -2 and -1, and I'll use those to rewrite the middle term. So minus 3y is the same as -2y plus -y. And I'm going through this key number method to factor polynomial, because I think some of you need it. From some of our discussion of limits, I was seeing that a lot of you forgot how to factor. And then when I factor by grouping, by pulling out a common factor of 2y for that guy, and here I'll pull out a common factor of -1, that's the smarter choice. And then notice that y minus 1 is common to both terms, and then boom, I have it factored, and now I apply the ZPP, also known as the zero product principle, to finish off solving. The ZPP says if something times something equals 0, one or both of those factors is going to be equal to 0. So I get 2 answers here. Uh-oh. Are both of them right? Yes. They're both good. Well, what does that mean? That means you're going to have 2 critical points, but you have to be careful. One of them has a y coordinate of 1, and the other critical point has a y coordinate of 1/2. How do you get the corresponding x's? Anybody have an idea? I'll open it up.
Yeah.
Plug them into the equation.
Gotta do that.
You could, but I don't think that's going to be the way to do it. Yeah, Adriana has it. Thanks, Adriana. You're absolutely right. I appreciate that. She's awake. Folks, what are you doing? Okay, do you remember when we were looking at those the system of equations, and we actually solve for x in terms of y? We got that x is equal to y squared. Sure you do. So you're going to use that fact that x has to be related to y, for at least this particular problem, as equal to y squared. Well, if y is 1, then x is also a 1. Yay! And if y is 1/2, then x is, woo, 1/4. So what do we have, folks? Right now, and I'll give you partial credit when you're doing one of these problems, is if you can at least tell me what the critical points are, I'll give you some partial credit points. Yay! And now the hard work begins. Are those critical points maximums, minimums, or saddle points, or what's going on with those? And how do you know? You don't guess. You don't go, well, I think that one's a max and that. No, you're not going to do that. It's not going to work. So the next part of this problem involves second partials. So you have to go form D, which is fxx times fyy, minus fxy getting squared. So you got to go do that. So you're like, oh man, second partials, and that's why I taught you when I did my videos for you, we did second partials. Okay, so fxx, how the heck do you get fxx? Well, you go to fx, which is this right here, and you take his partial with respect to x. And I get, what? Anybody see it?
Is it 2?
2.
2. Very good, just a 2. Oh, that was easy. Times, now let's get fyy. So how do you get fyy? Well, you look at fy, and you take fy's derivative with respect to y. And you get what?
6y.
Minus, and now you're going to get fxy squared, or fyx, because they're really the same thing. It doesn't really matter. Well, let's get fxy. So you go look at fx again. That's 2x plus 1 minus 3y. And you take his derivative with respect to y. And that is?
-3.
So if I clean my d up, and you always want to try to clean your d's before you actually use them, so things don't get too messy. And this d happens to only have a y in it. Does it always happen? No. A lot of times it's an expression in both x and y. But it's nicer. So now let's go test our critical points. Let's test the 1, 1. So if I evaluate d at this critical point 1, 1, what happens? I get a 3, which is a positive number. Ooh. Look at the theorem. What does it say if d is positive? Do I have a max or a min, or is it still not clear?
Not clear.
Not
It's
clear.
yet.
Because numbers 1 and 2 are both cases where d is positive. So the case 1, we have a min, but case 2, we have a max. So how do we make the distinction? It's going to be either a min or max, but what's going to be the deciding factor?
Whether it's fxx is less than or greater or equal. Less than or equal.
fxx.
I almost dropped a serious.
fxx evaluated at the point 1, 1 is going to be your deciding factor. Now in this problem, it turns out that fxx is a constant. That doesn't always happen. But the fxx for us is a 2, which happens to be positive. So what does the theorem say if d and fxx are both positive? Do I have a min or a max? Check the theorem.
It's a min.
Good, it's a min. Because both of those guys are positive. So you're going to have a min if you have both of those guys positive. So what can we say? We can say that the point 1, 1 is a relative minimum. Now, folks, I usually ask you to get the ordered triple, and so you may be asked on my math lab also, like, what is that minimum value? So the min value of this rel min is the original function evaluated at the point 1, 1. Which would be, oh dear God, 1 cubed plus 1 squared plus 1 minus 3 times 1 times 1 minus 5. And so that actual min value corresponding to our min, and this is just the z coordinate of the point on the surface, would be -5. So the point 1, 1, -5 is your minimum point that lives on the surface. So you have a little valley there, a little divot. Now what about the other critical point, the 1/4, 1/2? You got to test him too. He's part of the mix. So what is d evaluated at the critical point 1/4, 1/2? I don't know, plug it in. So when you plug this point into your d, let's see, 12 times 1/2 is 6, so I get 6 minus 9, but that's equal to -3, and that's a negative number. So what does the theorem say if d is negative? Check it.
It's a
There's
sad
a relative maximum.
Careful.
Oh,
D
wait. Oh,
is
shoot. Whoopsie.
negative.
Uh-oh.
Saddle point. Woo! So you don't even have to go check fxx. Who cares? So you have a saddle point, neither a max nor a min. And so the saddle point, and if I like to see order triples, that occurs at the order triple 1/4, 1/2. And if you plug 1/4, 1/2 into your original function, you're going to get -79/16. I know. And we are done with this problem. So congratulations. You have now seen finding extrema, relative extrema for functions of two variables. And it's really cool. And by the way, business calculus people do this also. Like they actually study a little bit of multivariable calculus and they learn how to find partial derivatives. They don't learn about directional derivatives or gradients, okay? They do not do that at all. They go straight from learning the partial derivatives section right into finding extrema. And we will be doing some business calculus applications, because I used to teach business calculus quite a bit some time ago. And I think that you should know a little bit about business calc, because if they can do those problems, you can too. So we'll be doing some problems with profit and revenues and costs, and knowing the relationship between profit and revenues and costs, because you should know what those are. You might own a business someday. I'm done. Bye. See you later. Anybody wants to stay for 5 minutes for quick questions, I'll be there. Otherwise, I'll see you in my office hour today at 1 o'clock, or I'll see you Friday morning. Bye.